Good afternoon, class. Today I wanted to go over the last chapter section of chapter 12, which corresponds to the material that we missed in our main lectures because I had to cancel, and it was just before the university closure of classes. So in chapter 12, we were looking at the worker safety rating data where observations or employees were categorized by their job being either unskilled, skilled, or supervisor. And then what was being measured, so this sample means and standard deviations were from the worker safety ratings based on a survey that these participants participated in. So in this example, what we had done was an overall F test from our ANOVA table built based on these data, and we found that there was a significant difference in the mean rating across these three different groups, but what we didn't know was which groups differed or or how large those differences were. So we talked about contrasts that we could do to look at specific comparisons, but what we hadn't worked through was an example of looking at all pairwise comparisons. So this is what I wanted to talk about today. This is take 4 of this video, so let's hope that it goes smoothly. So looking at our multiple comparisons, we have I equals 3 groups. Which implies that there were I choose 2 equals 3 choose 2 equals 3 pairwise comparisons to be made. And so the comparisons are going to be, so I'm going to make this a little bit larger. One is comparing groups 1 and 2. 2 is comparing groups 1 and 3. And 3 is comparing groups 2 and 3. And what I want to point out is that in the null hypothesis, we have mu1 equals mu2 versus unequal. We're doing two-sided tests. So even though this says, so this is T1, 2, it doesn't really matter whether you took the difference the other way around, like took x bar 2 minus x bar 1 in a practical setting, because the test statistic will have the same magnitude, and the magnitude is all that we need in order to actually do a two-sided test, right? So the difference would be negative if we took the difference the other way around, but our denominator would still be the same. So in the first setting, what do we have? In the numerator is our contrast being the difference between them, and in the denominator, we have the standard error of that contrast. Okay, for these data, if we look back at the original summary statistics, here was our sample mean for group 1, the sample mean for group 2. We see that the ratings for group 2 were a little bit larger, so we're going to get a negative value for the difference. And the standard error is still this pooled estimate of standard deviation, which we calculated as the square root of the mean square error. So I'm again flipping back to page 114, we found the the mean square error to be 326.65. This was our SP squared, so the square root of that is 18 point something. And so our test statistic is pretty close to 0. When we go through to do our test, we'll see if it was close enough to be not significant. In the second comparison, we're comparing groups 1 to group 3. Since the rating for group 3 is higher than that of group 1, we again get a negative test statistic, but this time it's larger than what we had comparing the unskilled to the skilled workers. This one is the unskilled to the supervisors. And then for group 3, what we have is comparing the skilled workers with the supervisors. And because of the way we took the difference, the supervisors have a higher rating than or mean rating compared to the skilled workers. So again, we get this negative test statistic value. So usually what we've been doing throughout this course is saying once we have a test statistic value, let's calculate the p-value. But in all three of these tests, they're going to be compared at the same level of significance. So say 0.05. So for alpha equal 0.05, if we think about it, that's our t distribution. And what we have up here is our alpha over 2 for a two-sided test. And if alpha is equal to 0.05, it's going to be 0.025 for a two-sided test. And the t star value is the t value that corresponds with this alpha level. Sorry, that should be a 1 star. Okay, so that's our t star value. And so when we do these tests, what we could do is calculate the p-value and compare them to 0.05. But the p-value might be different for each one of those tests. However, the t-star value is the same. So it's actually faster. Here we only have 3 comparisons. If we had more, generally it's faster to compare a test statistic value to our t-star value. And note, if our test statistic value was greater than this t-star, then we would be somewhere inside here, this critical region. And so we know that although I don't know what the p-value is, I know that it's going to be smaller than my alpha level. On the other hand, if the test statistic value was less than my t-star, again, I don't know what the p-value is, but I do know that it is greater than 0.05, which means I'm going to have evidence to, and so just to complete this, I'll put this down here, alpha over 2, which is 0.025. So what I do know is that if I'm only interested in whether a test is significant or not significant, and I'm doing many of them, it's just faster to compare to one t-value that rather than computing these different p-values. So here is our least squares difference method and our Bonferroni method. Both of them use the exact same test statistic values. What differs is the critical value of what we consider the rule of whether we just deem a test significant or not. So the least significant difference compares to that t-star value, as we mentioned. And in here, we're essentially ignoring multiple comparison issue. For the worker rater the safety rating example, the t-star is based on 587 degrees of freedom. And then from table D, we can look up that we get a t-star value of 1.984. This is actually based on degrees of freedom equals 100 in our table. It won't be that much different, though, because our degrees of freedom are already so high. The actual t-star we should be using. From software, you could get a more exact one. And if we do the comparisons, remember this is the absolute value of our test statistic comparing groups 1 to group 2. And we see that 0.38 is less than 1.94. So we say that groups 1 and 2, the skilled and unskilled, are not very different from each other. Comparing groups 1 and 3, the test statistic or its magnitude is 3.7776, which is greater than 1.984. So we will say that groups 2 and 3, 1 and 2, groups 1 and 3, the unskilled and the supervisors are significantly different. And then the last comparison is groups 2 and 3. We get a test statistic value of 2.94, which is greater than T star, and these are different. So you can see that this is much quicker than calculating 3 different p-values. And in words, then we say that unskilled workers and skilled workers are not significantly different with respect to mean safety rating, while unskilled workers and supervisors are significantly different, and skilled workers and supervisors are significantly different. Now, in this example, we did not account for the fact that we were making many comparisons. Remember that when we make multiple comparisons, so go back to thinking what our alpha level actually means. If we had done our study many, many times and then conducted our test, we set an alpha level of 0.05, then we expect that 5% of the time our test might come up significant, even though there is no difference, just due to chance. So it turns out that on the same data set, if we make multiple comparisons or perform multiple tests, we run into the same issue that if we make enough comparisons, some of them will come up as significant, even though there is not a difference just due to chance. So the Bonferroni method is just one of the ways we deal with it. And we go over this one more or less because it's a simple one to account for, to deal with, to calculate. So for the Bonferroni method, what we do is we say, look, overall, we want our test to be significant at this 0.05 level, but we want to account for the fact that I'm doing these multiple tests. So as a family, I want it to be 0.05, but on the individual level, I'm going to partition that 0.05 equally across each of those tests. So each test is going to have a more stringent alpha level, which corresponds to having a lower alpha level. So our alpha star star is equal to alpha over the number of tests. For the worker safety rating example, T star star again is still based on 587 degrees of freedom because our test statistic had 587 degrees of freedom. But our alpha star star is not 0.05, so that the individual level, we're doing it as 0.05 divided by 3. And at this point, it gets harder to use our statistical table. So we're going to rely on software to get what the T star star values are. It's 2.40. And again, the test statistic values are the same as what we used in our least significant difference. There's a typo here. But we come to the same conclusions, that the skilled and unskilled workers are not significantly different from each other. The unskilled and supervisors are significantly different, as are the skilled and supervisor groups, significantly different from each other. So the conclusions are the same as you get from the least significant difference for this particular example. And this might just be a sign of that the differences were strong enough. It didn't matter with taking the multiple comparisons. And it's also tied in with the fact that we only had 3 groups or only 3 comparisons. If we had 6 comparisons, 10 comparisons, 1,000 comparisons, you could imagine that the 2 different methods could come up with different tests being significant or not significant. I also want to comment that if you're using this one-way analysis of variance in SPSS, there is a place where you can check the method, being LSD or Bonferroni, and then it will give you back the test statistic values for the comparisons and the p-values. And actually, you would have seen that in the output from your last assignment. Okay, so we know which groups are different. What we don't have a handle on now, what's remaining, is just how big are those differences. So that's what these simultaneous confidence intervals are for. And they're called simultaneous because we want to make sure that at our nominal level alpha, all of these confidence intervals simultaneously capture the true differences between the groups. So the big difference from, say, using those contrasts, specific contrasts, is that we are using a T star star value instead of T star. In other words, for each confidence interval, we are going to make it a much more stringent confidence level compared to what we were doing before, so that as a family, we have the confidence level we want. So here is how we calculate them. We look at the estimate of the difference plus or minus that critical value times the standard error of the difference. Okay? And for the workplace safety example, we found our T star star to be 2.40. So for a 95% confidence interval, we calculate the difference in the means, plus or minus, that's the T star, that's our SP, and this is the square root of the sum of 1 over the sample sizes of the group sample sizes. So we come out with a margin of error of 4.9876. And what we see is that the CI, SCI, so simultaneous confidence interval, covers 0 as it should, since the two-sided test was not significant. Okay, what about the other groups? Well, if we look at both of them, there are a couple of comments to make. First of all, if we look at comparing groups 1 to 3, we see that we have a negative interval. So, and then in 95% confidence interval for 2 and 3, we also see we have this negative interval. So, we see both intervals fall below 0. So skilled and skilled workers and supervisors, so we'll say categories, had higher let me see, what does this one say? So the skilled, the supervisors had a higher, so supervisor category had higher ratings compared to the skilled and unskilled workers. Okay, so this one was looking at unskilled to supervisor, and this one was skilled to supervisor. All right. What we also see is that it looks like the difference between the unskilled to the supervisor, that one's actually, if we compare this, minus 3.68 is less, it falls between this interval, and so does that one. So the unskilled to the supervisor is a little bit narrower, and it's actually covered by this confidence interval as well. And again, that might not be that surprising, because the skilled and unskilled workers were not that different. So there might be a good chance that the magnitude of the difference, if skilled and unskilled are the same, then you would expect a significant difference between the supervisors, and for that difference, the size of that difference to be the same. Okay, so this is just sort of reflects that as well as a side point. But when we look at it, one of the main things is that they don't cover 0, so there's a significant difference. And because they are negative, we know that the supervisors had higher ratings relative to the other two groups. Okay, so that is all that I wanted to cover on the one-way analysis of variance. And I think up to this point, we've covered everything to the end of randomized complete block designs. Next lecture or video will be starting material in chapter 13. However, your test 3 goes up to the end of randomized complete block designs. All right, see you guys next time. Bye.